going to be the same for almost all containers you ever come in contact with. The stuff that differs is the smaller part of most images. So if you use this scheme for delivering container images, you can do this very efficiently because you just have this big repository of chunks. You can put them on a CDN, and then every host that actually wants to download them can look what it already downloaded, and only the chunks that are missing it will download, and again in a very CDN-friendly, very efficient way. I personally think that's a major benefit over how containers, for example, do things right now, because right now containers generally, they always work with tarballs, right? If you do a Docker container install today and then update tomorrow, it will download the tarball usually, or at least like with the layer stuff they have, but that's mostly version control, not so much about actually reducing the delta. So yeah, long story short, it allows you to systematically minimize the place of disk you need to store these images, and it minimizes the amount of data you actually need to transfer. I have been talking a lot about containers now, but the same thing if you build embedded hardware. If you build IoT devices, same thing. And actually even matters a lot more there, because IoT devices usually have very little storage. IoT devices have very little, like internet connection is usually very, very slow. So for them it really is important that when you do an IoT update like every week, that it doesn't end up always downloading the full tarball, but simply downloads just the chunks it currently hasn't on disk anyway. Yeah, why again this? When acquiring a new version of a file system image, we can process one or more existing old versions with the algorithm first, and we get a pool of reusable chunks. This is awesome for IoT basically because, I mean, in IoT you usually have the scheme where you have two operating system images, like one called A and one called B. You boot up A, and then B is the one you update. And then after you update it, you boot it to B, and then you can update A, and so you always have this A-B update scheme. Because of that, you always have a complete OS image on disk, and you can always use that as a pool for chunks, so that if these chunks already appear in the version that you want to upgrade to, you don't have to download anything. So you have automatic, robust reusing of what was downloaded before. This is actually really, really interesting, because this stuff works without any developer or whoever, like technical person, actually calculating any deltas for you, right? There are a couple of IoT and container image update systems that work around deltas, right? Where they basically say, yeah, every day we give you the new tarball of the OS image, but we also give you a delta, like basically the difference from today's image and from yesterday's image. This is an efficient way to do updates, right? Like because you only need to download what actually has changed. But it also comes at a price. The price is twofold in particular. One, you actually need to pre-calculate these deltas, right? You need to know what kind of upgrades are my devices going to make. Are they going to do update daily? And if so, then I have to upgrade between like every single version. Or are some of them going to update monthly? And if they do, then I have to, in addition to the daily deltas, also calculate the other ones, because otherwise they have to download all the deltas and apply them one after each other, which is not going to be much more efficient eventually than downloading the new image. So you need to know in advance what delta you have, and if you actually want to provide all the deltas, it grows exponentially, right? So this stuff doesn't need that, right? It's completely automatic. If you have the data on disk, it will use it. It doesn't matter if there's any historical relationship or not. It just finds them and uses it. Yeah, so that's actually a major benefit that I see. For example, other systems like the OS tree thing, like OS tree, I'm not sure if you guys know this, is a delivery system for like Flatpak, you know, this GNOME application logic that uses OS tree in the background, and that is built around deltas, and they basically have to pre-calculate every possible update that the user wants, and if that doesn't work, then it becomes very inefficient. Yeah, what's also kind of interesting is that this is so good because it automatically recognizes similarities through the hashing and blah, 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 that you can actually do upgrades like cross-grades between two unrelated trees, right? For example, you can use the chunks that you have on disk from a Fedora container image to upgrade to Debian container image, and it's going to work. The reason for that is like that the Debian and Fedora images actually share a lot of data. Time zone data, locale data is exactly the same on disk on Debian or in Fedora. And even though there is no historical relationship between the two distributions, this algorithm will automatically recognize the similarities and reuse whatever you can reuse. So this is kind of awesome, right? No revision control necessary, no history relationship. What is similar is recognized. What's also, like if you compare how Docker delivers images, what's also really important is, I personally believe, like, I mean, Docker has a scheme where you basically, you put together a container and then you commit it, and then you make the changes and you commit that again, and every time you do that, it creates basically a delta table. To me, that's revision control. Yeah, revision control to me is something that a developer wants, right? You want to be able, that's why we all use Git. You want to be able to look into what you did last week and what you fucked up back then, and want to be able to fix it, right? But to me, revision control is something that should stay something that only the developer sees, right? The actual deployment on a server should not have revision control. It's not relevant. The development work, how the developer originally, what bugs he added and what he later fixed. What matters on the deployment is actually just the new source code ends up there. In Docker, these two things are like intermingled, right? There is no distinction between minimizing upgrades and doing revision control. It's the same thing. In this scheme, if you deliver images like this, there is no revision control, right? There's only, like, if there's similarities, they are detected, and that's all there is. I know I talked about a lot of stuff so far. I wanted to say that if you have any questions, completely interrupt me, by the way. So maybe this is a good time actually to take the first questions if anyone has anything. I hope you guys could follow what I was mumbling here. You have a question. I think there's a microphone, and I think it's recorded, so I think it matters that the microphone's used.
Yeah. So, what about questions? Please raise your hands. Oh, okay. We have.
I mean, by the way, I have way more slides. It's completely fine if we don't go through all of them, but if nobody has questions, then we can continue with that.
Please.
Yeah. So the question is, you say that you remove file system boundaries, but this means that actually some chunks might have the ending of one file and the beginning of another one.
Yep.
And this means that actually, as far as I understand it, that some of those chunks will be used less frequently. So you will have larger sessions.
Yeah, so I first, when I serialize everything, I care about reproducibility, and that also means that I sort everything, right? So usually, if I serialize something, the stuff that is in the same directory, multiple small files get lumped together into one, right? And the thing is, like for example, if you think about locale data, time zone data, right? All the distributions actually carry that exactly in the same order, the same file. So actually there will be lots of reuse. But you're completely right. If sometimes it will happen that one file that is, I don't know, belongs to Apache is going to be lumped together in the same chunk with something that is completely unrelated to that, like so let's say MySQL, and then there might not be many containers that actually are able to share that. But it's, you know, I talked about this modulo calculation, right? This Q parameter. By selecting the Q parameter, this integer, if you make it smaller, you get smaller chunks, right? This increases reuse, but basically means you need to store more chunks individually. So you pay a little bit for the metadata because you have more metadata, right? But it basically, you have, through selecting the Q, you have the choice how likely, like how big do you want to make the chance for similarities to be recognized. Sometimes you might want to pick it big. In that case, the chance of reuse goes down, right? Or you can make it small and the chance of reuse goes up, but you pay for metadata, right? So the idea is basically, yes, this will happen. This will probably not happen as often as people might think, again, because most Debian packages, RPM packages, are sets of files that manage whole subtrees of directories, right? But when it happens, you have control how likely the tool will recognize similarities or not. I hope that's an answer. There are more
Just a
questions.
moment.
I have the next question. Sorry. Is CA Sync is mature enough to use in production as a backup tool? How do you think?
So it's no. The answer is no. It's like it's nothing like you won't find it in any commercial distribution yet. I think it works well for many cases, but in particular for backup. So if you do backup with it, you need encryption. And while I have my brother's a cryptographer, and I sat down with him and added, we designed all the crypto system for it, but I still haven't implemented it, right? So all of this works fine for delivering container images, IoT images, because you don't need to encrypt things, right? But if you do backups, you need the encryption, and that's not there yet. So it's this is technology that is not ready for production yet. I think it's very comprehensive, and it could be soonish, but it all matters. Of course, somebody needs to be the first one to actually deploy it, and then give us feedback and things like that. But yeah, if we can just be honest, it's not. Nobody else has used it in production that I know of. I know that a couple of container companies have played around with it. For example, the Facebook people have, because I'm one of the organizers of a conference in Berlin, All Systems Go, which is about low-level systems programming. By the way, you all invited, should totally come. But the Facebook people have submitted a talk at this conference in Berlin where they talk about using CA Sync for container delivery inside of Facebook. And I'm very curious about that, and that's what I know, that people have looked into it, but I'm not aware that anybody has already deployed it. It's a year old, right? It's not that it's very old.
May I ask
Thank you.
another question? I'm here.
Okay.
So returning back to the one previous guy about sizes of the chunks, does it make sense to actually choose the chunk, the size of page size of the memory mapping in kernel? Like 4K or huge page, 2 megabytes, I guess. Two choices.
So it's a good question how to pick the queue. I quite frankly don't know how to pick the queue. It probably depends on your use case, right? You should never forget, these are not equal sized chunks, right? And memory pages are equal sized chunks, right? So if you pick queue and say by average you want a 4K size, then this doesn't mean it will match to the memory stuff, because some are going to be smaller than 4K and some are going to be larger than 4K. How to pick queue, I don't know really. The values that I'm using there, I basically copied from some other project because they did the math and figured out what's right for them. It also depends on the data you actually want to deliver. I actually have a slide about this much later here. Let me quickly jump ahead to that. I thought I had one. No, I don't find it. Okay, this one. SquashFS. So if you do IoT images, people like to use SquashFS. SquashFS, for those who don't know, is a Linux file system that is read-only but compressing, right? So it's basically a tarball you can mount. Anyway, now SquashFS is awesome, but SquashFS has generally compressed data, right? If you use the chunking algorithm, the rsync algorithm on compressed data, it's not going to do any good for you. The reason for that is simply that I look for similarities, but a compression algorithm basically removed all the similarities. That's what a compression algorithm does. It removes redundancies, it removes similarities. So a perfect compression algorithm is not distinguished, the result's not distinguishable from randomness, and randomness is not going to have similarities. So in theory, you might now think SquashFS and CA Sync, they're contradictory, right? CA Sync is not going to do any good at that. In real life, that's actually not true. It actually is still doing good for you, because the way SquashFS works, because it's a random access file system, they don't have a continuous compression stream, but instead they compress block by block, right? So because they want to be able to randomly access like the file that is compressed like way at the end, and they need to find that, they actually go block by block. Now, the reason why I'm mentioning this right now is if you know that the data you're going to stick into the repository is going to be a squash file system, then you can sync up the average block size, the average chunk size that CA-Sync has for, with the block size that SquashFS actually uses for addressing stuff. And if you do that, then CA-Sync will be able to recognize the similarities again and again. So what I'm basically telling you is how to pick Q depends on your use case, right? We pick a default that has, like people have shown, is a good default, but it also depends. You know, if you have a CDN contract, right, with one of the big CDN providers, they usually pay, like you pay per retrieved object regardless of the size, right? So depending on the precise semantics of your contract, it might be more interesting to like ship larger objects and not care about the similarities, or smaller objects, right? Basically, the queue gives you a control how many objects are going to be retrieved by the clients downloading it, right? So, long story short, how to pick the queue, I can't tell you really. It's up to the user ultimately. We will pick you a good default that will probably work for most people, but depending on your CDN and what you put into it, can be something different. I don't think that the memory page size matters too much though, because this is stuff on disk ultimately, and so yeah, I don't think that would get you much benefit specifically.
Highlight, thank you for you have done. I mean, System D is just awesome and but there are some other projects you're related to. I mean, post-audio. I'm sound producer. I use open source free software to produce music. I record music, I play music, I compose music, and I use Audio, I use guitars, I use MC and other synthesizers, and I need Jack. You know Jack?
I know Jack, yeah.
Yeah, and Jack only works with Pulsar. And Pulsar audio is something that sits between and makes overhead, and it causes some unneeded.
Can we maybe talk about this after the talk, maybe? Because I mean, this is thank you very much for like, By the way, how much time do I still have?
Really short question because we have a lack of time.
Small question. I'm from Gray Virtualization System Company. We have a lot of devices with non-block device. And my question about, can we use K-Async to update our images? And C-Async will handle the situation when we have bad blocks on none.
You have what blocks?
Yes.
Bad blocks. So as mentioned, CA-Sync actually works on both levels, right? Like on the file system level, on the block level, and so you can synchronize XT4 images or SquashFS images just fine. But CA-Sync has no understanding, like it doesn't know what a bad block is, right? Maybe we can add this, but of course bad blocks, like what I care a lot about here is reproducibility, right? I want that the same file system tree or the same disk image, any time of the day, any time of the year, results in exactly what you want, right? And this goes through the entire design of the schema. For example, I have this slide up here, whether to use the classic Unix tar or not. My answer to that is not to use it. One of the reasons is, again, reproducibility, because tar does not generate reproducibility, like reproducible images. But the key that I wanted to say is bad blocks, right, are usually transient in some way, right? Like they're volatile. Sometimes you can read them, sometimes you can't, and hence they are a little bit contradictory to the concept of reproducibility, right? Because it's not going to be that one block is necessarily going to be bad forever, right? It depends on the specific machine, on the specific time of day, right? So we don't have support for that maybe we can add support for that, but I don't see how that fits together with the reproducibility, if you follow what I mean. Does that answer the question? I can't hear you like the microphone.
Maybe the last one?
Sorry. We have, for example, 200,000 devices in the field, and we want to deploy the updates to them. And what CA Sync will do if some device has bad blocks, some device doesn't have bad blocks.
Oh,
it
that's
will
what
validate the file system. The file system will be fine, consistent, and so on.
So CA Sync, every time it runs, will validate anything it operates on. Meaning, if one device has an incomplete update from yesterday or has a otherwise rubbish installation, right? CA Sync will first go through the file system, hash it all up, and if some of that stuff is rubbish, it doesn't matter, it will hash to a different result, right? And that basically just means CA Sync is not going to use that chunk, instead download it from the internet. So it's supposed to be very robust by the algorithms regarding what you have on disk. In fact, you can even tell CA Sync, please use the chunks in this repository on the local disk, and it has nothing to do with what you're actually downloading. It's entirely fine. CA Sync is not going to use any of those chunks because the hash is not bad. But it won't make it order forever because it does have to get excellent, but it won't hurt, right? Like the correctness is always ensured. We load down what's not available locally, and if what is available locally is crap, it doesn't matter. We will notice that and not use it. So that's way better than probably most of the other systems like this, because we always validate. We care a lot about reproducibility. That also means that if anything ran and updated in it, right, that it gets fucking guaranteed that it's exactly what you wanted and nothing else. And if it is something else, then CA will tell you so. Metadata. So when I serialize stuff up, I do store all the metadata, right? I care about metadata a lot. I care about metadata a lot than tar does, because I want complete reproducibility. And reproducibility is only provided if we not only replay the actual data structure, but also all the attributes of it, all the metadata. What I meant was that we ignore the file system boundary is that there are two steps. The first is the serialization. That serialization and deserialization, that does care about the file boundary. But then the second step, the chunking, at that point, I don't care anymore. At that point, for me, it's a perfect serialization, it's a perfect stream, and whether there are 3 files in a chunk or 1 file or 10 files, like the chunking algorithm doesn't care any bit, right? That's what I meant with this. But yeah, we do care a lot about metadata. We're exceedingly precise with reconstructing what we find on disk. Much more precise than tar or any other system like this that I'm aware of. For example, it saves and restores ACLs, which is actually something that tar can do, X address. And the chapter bits, if you know those, which are Linux-specific file bits, like .rfs information, like if something's a subvolume and things like that. You have, and moreover, you have a lot of control of the attributes that we save and restore, because depending on your use case, sometimes you do care about attributes being saved and restored, and sometimes you don't. Like, for example, if you distribute OS images, like container images, IoT images, you usually don't care about the modification time of the files on disk, right? Because, like, for example, you build your program with GCC, then if you compile it today or compile the same code base tomorrow, it should result in the same files. And if you compile it working correctly, that's what happens. But they will have different modification times, even though in every other way they are the same thing. So if you deliver OS images, you probably want to not serialize the modification times, because it basically just means that if you recompile everything tomorrow, the image will be completely different, right? So CA-Sync gives you precise control about the metadata to serialize and the metadata not to serialize. If I want to deliver OS images, I will turn off a lot of bits, like modification time. But if I do a backup of my home directory, I care a lot about end times, because it's usually very interesting to know what the OpenOffice document was that I edited yesterday and which one was the one that I edited 1 month ago. So yeah, I hope this makes it clear, and we care a lot about metadata, and we're much more accurate and much more precise with saving and restoring metadata than pretty much any system that I know, right? Docker, for example, has no understanding of whether it is a chapter or whatever else. And this is just a brief list. There's much more. If you actually type CA-Sync --help, you'll see the full list of attributes you can save and restore.
Well, let's thank Leonard for his talk. Now we have a really short break, and after that, file system mounts in user namespace will be just here. Two short announcements. The first one is for native